Swayam Prabha. Digital India. Educated India.
Hello and welcome back to this lecture series on foundations of cyber physical systems. So, we have been talking about these ideas on variable threshold based detectors, right. So, we said that it should be possible to change the detectors parameters based on the space in the trajectory where we are working, so that the attack detection accuracy increases, right. So, if we consider this windowed chi-square detector, the parameters of this detector was this threshold that we have been setting, and also this k-length window inside which this chi-square statistics was being computed. If you remember, this was my chi-square statistics, where sigma r is the covariance of the residue and Lk is the chi-square window, the test window over which I am summing up these different residue values. Now, from the mathematical machinery of chi-square, we can create this probability density function, where we can say that it is distributed with respect to this probability density. I mean, the distribution follows this expression, and the mean is m times Lk, where m is the number of sensors we are considering, and Lk is in the kth instant what is the window size of the detector we are considering. And from this PDF we can actually integrate it and figure out integrate it up to the threshold value for this kth iteration, whatever threshold we are setting for the control system's kth iteration, and we can actually figure out what is the CDF, the cumulative distribution function. That means, there is a probability that this chi-square stat is less than the threshold, and we can I mean from basic statistics we can see that this would be this kind of a nice well formed function, where these are the gamma functions. Okay. Now, we will cover these things a bit more detailed in our assignments and tutorials, where we will actually give examples of how these things really work. For now, let's just consider it in a formula in this form as is given here. So, these are the gamma functions, and you can see the parameters are the threshold, the number of sensors m, and the window length on which I am computing the chi-square stat here. Okay. Now, this thing we have already discussed that since I know this probability, so suppose there is no attack happening. So, 1 minus this that is the probability that Gk is greater than threshold is basically the probability of false alarm, and when there is an attack really happening, then 1 minus of this is the probability that there is a true positivity, right. Now, this distribution actually shifts and becomes a non-central distribution when there is no attack. This can be proved. We are actually omitting the proof here. All I am trying to say is, let us just correlate these expressions here with this picture here. So, essentially when I say that what is the probability that Gk is greater than threshold is nothing but the integration of this curve from threshold point up to infinity, right. And if the distribution is the green one when there is no attack, then you have this green part, and when there is an attack, then this distribution is for the true positive rate, and since the distribution is shifting here right to a non-central one, it is going to be is this part, right. Now, the question is what should be my target when I am trying to create a detector. I should try to create a detector which chooses its parameters of threshold, its parameter of window length in such a way that this thing happens. That means, the true positive rate's value is higher than the false alarm rate's value. So, that based on that actually we created this optimal threshold synthesis problem, and we say that what should be my parameters of this detector, so that this objective function gets satisfied. And accordingly you can also create this is my detector design problem, and if somebody is trying to design the attacker, then what should be the goal of the attacker? The attacker's goal should be that I want a lower true positive rate, a higher false alarm rate, and a higher estimation value, a higher value of estimation error of the state, right. So, suppose you are trying to create an attacker model and you are trying to say that what is the attacker, what is the amount of attack that this attacker is going to inject. So, it can be found by maximizing this cost function, where what is this cost function doing? It has made suitable choice of W1, W2 and W3 these weights, right. So, these are scalar weights and this is the matrix based weight. Okay. And what it is doing is, well, it is saying that, well, choose this in a way that so that these W1s, these W's are positive and positive definite here. So, that the attacker will try to give weightage to decreasing TPR, increasing false alarm and increasing the estimation error here, right. So, that is how the objective function is designed, and of course, all these choice of the attack values have to be such that you satisfy these constraints, right, because these are the standard control system constraints you have for the dynamics of the system. So, while satisfying all these constraints, if you can choose suitable values so that this cost function is maximized in every kth instance, then you can have a suitable value of the attack vectors which are which have a higher probability of bypassing the detector, right. So, actually that is how it works, because based on this, so that means you have to solve this complex constraint satisfaction problem in every iteration of the control system. That means, in every iteration you have to set up this objective function and solve it with respect to all these constraints, and accordingly you get the values of attack values on the measurement and the control input. Now, the thing is, this is the complex situation, right. I mean, solving this has to be done in real time, and accordingly the attacks has to be injected with almost no delay. That is virtually impossible. So, that is why we said that, well, let us have an AI agent which learns how to attack and which also learns how to detect. So, that means, if you are trying to create an AI agent which is trying to learn a detector, you should make the detector learn over an attacker agent's attacks also, right. That means, you should create a nice attacker agent, and you should see that the attacker agent's goal is to disturb the function of the system, and the detector should be able to learn what should be the threshold based on which it can detect the attacker this attacker agent's attacks that they are causing, and in case this detector agent is able to detect the attacks, then it can be deployable, and in a deployed scenario it can actually subvert other attacks also, right. So, we actually formulated it as a multi-agent reinforced learning system. So, as we know that a reinforcement learning system is basically a very popular AI technique, where you are trying to learn some way to give actuations to the environment, but the environmental model is quite unknown to you. So, it is like thinking that, well, I am trying to design a controller for a plant for which I do not really have a model. That is why RL based techniques have found in recent times lot of applications in complex control design problems, where you do not really have a nice model of the plant, right. So, just in a nutshell, what the RL agent is supposed to do is, it is trying to test an action, and accordingly it will receive a state update that, well, the environment changes a state from this to this, and you get this kind of reward, right. And if there are multiple agents, each of them have their own actions, and based on that they can observe their rewards, and accordingly the agents learn that, well, what should be its optimal action, so that the rewards are kind of maximized. So, in this case, if I try to map it, for an attacker, it is trying to generate actions like AY and AU, and what it is trying to observe as reward is, well, what is the maximum amount of error I am able to induce into the estimation, and whether I am able to create stealthy attacks in the process. So, based on that, you can just create this kind of agents, one agent for the attacker and one agent from the detector. As you can see that this attacker, what it is going is, it is trying several is going to try some ad hoc actions initially, and then it will observe, well, what is the measurement, what is the control input, what is the chi-square statistics, etc., and accordingly it will evaluate this cost function that we design, and this cost function is rewarding the positivity, negative, I mean decreasing of true positivity, and increasing of false alarm rate, and increasing values of the estimation error, because this is from the attacker side view. if you see the detector's cost function, what are the detector's choices? The detector is trying to set suitable parameters for the detector. That means the agent for the detector is trying to set suitable parameters. That means it is trying to choose a THK and a LK, so that after it observes that one closed loop control iteration, it is trying to figure out whether what happened to the system, what is my calculated TPR and what is my calculated FAR based on the previous formulas we discussed, and if there is a gain in TPR and a decrement in FAR, it is going to reward it as per this formula, right. So, this is how the RL agent will work here. It will try to maximize, it will try to reward the detector RL agent if it is able to increase TPR and decrease FAR, and the agent for the attacker, it will try to it will give awards to the attacker if it is doing the opposite, and also in the process it is going to increase the estimation error, because that is the objective of the attacker, right. Now, if this game is played between the agents in a simulated environment, we actually have examples of how to create such simulated examples in OpenAI Gym and similar simulators, but that is an advanced stuff. It will be only I mean, we are not going into the details here. We are just trying to motivate you to think that this is indeed possible. This kind of CPS security problems can be mapped to AI problems, and if you are interested, you can actually model it in a AI simulation environment. So, that is how a control problem can be mapped to an AI simulation environment, and you can learn control actions, you can learn protection methods, that well, for this system for which I do not have an attack model, if I use this kind of an attack agent model where I know the reward function and stuff, what will be the lethal attack that the attacker agent can then learn, and based on those lethal attacks how they can be prevented, that the detector agent can learn. So, that is the point we are trying to make here through this example. The next thing we talked about was this CAN based attack detection techniques, right. If you remember, we talked about what are the ways in which CAN buses can be actually attacked, right. CAN based systems where you have multiple ECUs, they can be attacked, and one ECU can be thrown, a victim ECU can be thrown to a bus off mode, right. Now, the thing is, well, if we have residue based detectors, now let us think that you have a control system implemented over a CAN. That means the packets, the measurements and the control actions are moving over the CAN bus as a packet, right. So, what I mean, in our previous example of residue based detectors, what we did, we were computing these estimates and the estimate error, and we are trying to detect whether an attack has happened or not. Now, there is something different we can also do based on the architecture of the system. So, your architecture of the system is, well, you have a CAN, here you have a plant, here you have a controller. In our previous system, that is this, we had the controller and also a detector, and whenever your measurement came here, you fired up the detector earlier and you calculated an expected measurement value, right, and you saw that, well, what is the measurement you are getting, and you do a difference here and see that, well, if that estimation error is higher from the threshold based on chi-square statistics or norm based detector, whatever you are using, and you say that, well, there has been an attack or not. But you can do something different. In this model, you are assuming that the attacker knows what is the plant, what is the controller, what are their periodicities, and exactly when these values, that means the plant measurements are moving from the plant to the controller, and exactly what is the period and offset with which these values from the controller to the plant, those control inputs are moving. So, that can be a very ambitious attack model which may not be true. Alternately, what can happen is something like this, that, well, suppose I decide that, well, I will change the rate of the controller, and this is something unknown to the attacker, or the plant and the controller has a mutually agreed upon schedule, and in that schedule it is dropping the measurement communication or the control input communication in certain cycles. If that is the case, then if an attack is happening at those points, they will be detected, because we get a value at a point when I'm checking and I'm figuring out that there is a CAN message with an ID, because of the attack, but this message was not supposed to be there because the controller knows this is not a time when that value is supposed to come. So, if a controller and a plant decides on such aperiodic schedules, then there would be some ways in which the attacks can be detected here. So, let us see such an example. So, this is what we call aperiodic control execution or skipping of some control execution rates. So, whatever we discuss here, mind this that they can also be achieved by having a controller which has a modified rate, that an adaptive rate. That means, you have the plant, you have the controller. Let us say the controller is sampling at rate h1 now, and then suddenly the plant is being sampled at rate h1 and then at h2, and accordingly with that in synchronicity the control updates rate is also changing. Now, if this switch of rates is not known to the attacker or the attacker is unable to guess that, right. So, then that can also be a way to detect attacks, because suppose I suddenly change the rate from h1 to h2, I know that then at a modified offset and timing the CAN packets are supposed to come, but if the attacker does not know that, then he will be sending the attack packets exactly at this period and they will be detected, because those are. So, basically that is a timing based detection. You know that at these points no CAN packet is supposed to come, but if I get a packet, that means there is an adversary existing in the network. So, let us talk in general about aperiodic execution or skipping of some control execution, which I said earlier, that at certain points of time, if you understand that, well, this change of rate can also be modeled as aperiodic execution. So, what I mean is, let us say I am working with a sampling rate of h, and suddenly I increase that rate to 2h. Then if the attacker does not know this, then he is attacking here and he is getting caught. This situation of modifying sampling rates in general can also be talked about as skipping of control execution. So, let us say I do not change the rate, but rather this is like a sequence of ones, the positions where I am sending the controls, but later I started introducing some skips. That means, I started saying that, well, in this next control cycle I do not send the control packet or I do not use the measurement. Similarly here, stuff like that, right. So, if you do such kind of skippings, then what you have is an aperiodic control execution. That means, let us say I decide that, well, I am operating at this period h, this is all h, but like I said, here I take the measurement and the update, here I take the measurement and the update, here I do not do anything, here again I take the measurement and the update. So, it is like a binary pattern of 1 1 0 1, and I am saying that, well, I will repeat the pattern. That means, I am saying that, well, inside the pattern I am not doing, I am skipping the control execution and I am skipping the measurement gathering process in the every third instance of a 4 length pattern. So, this is what is our idea of skipping control executions, that we decide that there are certain points when I will periodically change, I will just drop the control action, okay, and I will just also drop the measurement, because if I do not compute a control action, I do not need the measurement. But the thing is, the trick is that the attacker should not know this, okay. So, then for the attacker, analyzing the schedule and identifying when to attack becomes difficult. So, because the attacker does not really, because you see in case of bus off, the attacker has to analyze the schedule and figure out when the controller or the plant is sending a measurement or actuation packet, right. Now, if occasionally I have this kind of drops, then for the attacker figuring out those attack points is immensely difficult, right. So, then in that case there will be failure to synchronize and launch bus off, and also even if they are able to do that, the attacker may resort to sending packets at positions where the controller and the plant knows that there should not be any packets, because we have decided to skip those positions. So, let us take this example. Suppose we have this kind of a skipping sequence. That means, we have decided that, well, we will we will execute control here, but not at these points, and then again at these points. Okay. So, that means I am taking some measurements on the bus. Okay. So, the way we are showing this thing is we are kind of we have this packet here, that is a measurement packet, and accordingly control action is computed, that is kind of denoted by this one, and accordingly control input value is again sent as a CAN payload over the bus. So, this is the control unit, this is your plant actuator sensor system. So, the sensor senses this value. So, let us say this is y1, and accordingly the controller sends it this a1, because the y1 has been used, this packet has been consumed, there has been computation and an update here. And then there has been y2, and accordingly this has also been computed, right, and this has also been sent. So, you have a2, right, but then you decide not to send, because your schedule says that, well, let us not do any communication in the next 2 cycles. So, there is no communication for y3 and y4, okay, and accordingly on the controller side there is no reception and control input computation, right. So, these things are not computed. Okay. So, accordingly I have a2 holding up here, right, the actuation, or let us call it I mean if I just write it here in terms of the use, this is my y0. Okay. So, for a minute let us just use my notation that I have already here, right. So, I have a y0, and based on that you have u0, and then you have computed u1, but here you do not compute u1 or u2 or u3, right. So, that means what you are doing is well, you are just holding on with this u1 here and here, right. So, if I see here I had my actuation a1, then a2, in the next 2 cycles I do not update the actuation, it remains a2 and a2 only. Okay. So, that is the thing, I do not update the control. Now, again I have a 1 here. So, that means I will take some value here, accordingly I will do some control input calculation here, right. So, that will update this, right. A new control has been calculated and the actuation is updated. Again maybe there is a skip. So, this a3 will continue, and then again there is actual computation with this measurement, there is a computation and there is an actual control action moving. So, you have a5. Okay. So, as you can see what is happening is you have skipped certain communications on the bus, both from the plant to the controller and the controller to the plant. Okay. And we are representing this phenomenon in a shorthand using a binary stream. So, what this means is there is no sensor data reception and there is no control execution and transmission during this thing. Okay. So, if we do this, what is the advantage? That is the thing, right. The advantage, as we have been saying, that there are twofold advantages. One is the attacker, when he is doing a schedule analysis of whatever CAN traffic you can see on the bus, and he is trying to guess that, well, where to attack, it will be difficult for him, because he will be having difficulty in figuring out exactly at what point the attack injection must be happening. Now, they also are smart. So, what an attacker can do is, attacker will launch an attack when a high priority message is on the move, because that cannot be prevented, and then immediately after the high priority message, the attacker's message is queued, and then it will be transmitted in sync in the next period with the victim's message, right. So, that is how the bus of attack works, that you target a high priority message, the high priority message will not let you go, but you will be queued, and that means now you have a synchronization point, because you know that the moment this high priority has gone, the victim's message, which has same priority as mine, whenever that will get access to the bus, I will also get access to the bus. So, let us say here you have the attack message which is synced with the victim, and these are the instances of the victim message, and you are again targeting this victim message here, and you are launching the bus of attack. So, what will happen is eventually the attack message will get synced with the victim message. Now, when you have these skip instances, so right. So, let us say before this skip instance, the attacker has queued a message with respect to high priority message, which was here. So, due to this high priority message, the attacker's message could not be sent, but it has got queued, right. So, the moment this message finishes, the attacker's message now goes, but on the controller it will receive this message, right, because but it knows that at this point I am not supposed to send any message, I am not supposed to receive any message, right. So, it will detect that there is an attack happening. So, that is a nice technique through which attacks can be detected in a system by actually deciding that, well, I am not going to send control updates in a regular way. I can either make the controller aperiodic, that means the controller switches its period and according the control gain value after some times which have been pre-decided, and the attacker does not know that. So, when the attacker will continue in the old rate or old speed of control, eventually it will be detected. Or we do not change the controller's period, but what we do is at certain periods or certain cycles we are not sending any message at all, that is pre-decided. But now, when the attacker is going to send a message, that is the only message that will get queued, because the victim is not sending anything. So, it will be detected. So, that is one way to look at it. Now, with this maybe we will end this class, and we will resume again with our next topic in week 12, which is attack mitigation strategies. Thank you for your attention.